I am super excited to be here today to talk about Delta Lake, and specifically how Delta Lake can help bring reliability to your data lake. But before I get into that, let's see if I can get rid of the tech alert chat and make this work. Perfect. So before we get into that, I want to talk a little bit about why people are so excited about data lakes in general. What is this technology? Why are people spending millions of dollars on it? And also, why do a lot of these initiatives fail? So to get started, what is the promise of the data lake? As far as I understand it, the idea is this. You have a lot of different types of data. It could be customer data, it could be telemetry, it could be metrics, it could be console logs, it could be unstructured things like video and images. And the nice thing about a data lake is you can just store it all. It's just a file system. It's not a database. You don't have to spend a bunch of time ahead of time coming up with a schema, doing ETL, doing all these complicated processes to ingest the data. You just dump it there. It's just a directory in a file system, and you collect everything. And that's actually really valuable because sometimes you don't know what's going to be valuable until later. And so making it really cheap to collect things is actually useful. And then once you've got it all stored, the idea is you're going to do data science and machine learning. You can do really cool things like build recommendation engines. You can detect fraud. You can do predictive maintenance. You can even cure cancer using advanced genomics. However, I have some bad news for you. And that is your data is almost certainly garbage. Somebody upstream from you changed the date format without telling you. Some records are missing because the machine was out. Something's missing data because you haven't joined it yet. And so that means that the data stored in your data lake is also garbage. And now you have this garbage in, garbage out problem where your analyses are also garbage. And so I have seen this pattern over and over again where people try to work around the quality issues in their data lake. And I want to talk a little bit about the architectures that I've seen develop. So the problem is this. It's pretty typical. I bet many of you actually have done this as part of your job. But my boss came to me and said, you've got a bunch of events. They're coming in from Kafka. Or it could be Kinesis or S3 or anything like that. And you have two jobs. You want to do streaming analytics, so you can understand what's happening with your business right now at this very moment. And you also want to do AI and reporting, where you take a more longitudinal view. And you actually look at a long history of time so you can make predictions about the future. So I might be a little biased, but when I'm given a mission like this, I'm going to start by using Apache Spark. So Spark has streaming APIs. It supports event time aggregation. It has native connections to both Kafka and Kinesis. And so you can produce your streaming analytics pretty trivially. But that brings us to challenge number one, which is historical queries. Kafka and Kinesis are great for storing a week, maybe a day of data, maybe a month at most, but you're not going to store years of data in these systems. And so people often do this thing. I read a lot of blog posts, and I tried to figure out what to do here. I've heard about this thing called the Lambda architecture. And as far as I can tell, the idea of the Lambda architecture is we're just going to do everything twice. We'll have a separate system for batch, and we'll do streaming one way, and then we'll save everything on HDFS or S3, and we're good to go. From there, we add that to our architecture. It's a little bit more complicated, but that's OK. We're engineers. We can handle this. And once we've got the data lake, now we can do AI and reporting, right? Well, of course, it's not that easy. This brings us to challenge number two, which is messy data. As I mentioned, your data is almost certainly garbage when you first get it. Without some cleaning, you're going to have incorrect analyses. And so what I've seen a lot of people do is you start doing validations. So you write a whole other set of Spark jobs whose only job is to look at your data and tell you what's missing. Count how many nulls there are, count how many distinct values there are, make sure that this thing is actually correct. Send me an email when it's wrong, and I'll go in and fix it. So it's another complication in our architecture. Because we did the Lambda architecture, we have to do it for both batch and streaming. But that's OK. We have unified APIs. It's not too difficult. We add it to our architecture. That brings us to challenge number three, which is mistakes and failures. So validations are great, but something bad already made it into your data lake. And so now we need to clean that up. And like I mentioned before, this is not a database. It's a file system. So how do you do updates safely inside of a file system? You want to be very careful not to crash in the middle, because you might actually corrupt the data that's there. So again, a pretty common pattern. I'm sure many of you have implemented this in your companies. We're going to partition it. We won't have just one giant directory. We'll break it up into partitions by hour, day, month, week, whatever makes sense for your scale of data. And we'll build an engine to do reprocessing. So when something goes wrong, rather than recompute the whole thing, we'll just delete that directory and recompute that directory from scratch. So with partitions plus reprocessing, now we can handle these mistakes and failures. That unfortunately brings us to challenge number four, which is updates. So GDPR happens, or something like that, where you actually need to modify your entire data lake. You need to do change data capture. And so now your partitions aren't going to save you, because you actually need to modify things across many, many different partitions. Again, we're good engineers. We can solve this problem. We'll create a whole nother set of Spark jobs to do updates and merges. We'll be very careful about failing in the middle. Maybe I've even seen people do things like copy their entire data lake when they want to do GDPR once a month. Just copy everything, because that way if it crashes in the middle, it's very easy to recover from. So we can add this up, but again, you got to be very careful. Don't let these jobs run at the same time as your other analytics. You don't have isolation. So if you're modifying it while people are querying it, they'll get the wrong answer. So we'll make sure to run our GDPR jobs at 1 in the morning, and then everything else can start at 2. That GDPR job had better not be late, otherwise we'll get the wrong answers, but that's okay. We can do this. It's pretty complicated. But the problem here is, what you see is, you're wasting a lot of time and money solving these well-known systems problems, rather than doing what you really want to do, which is extract value from your data. And the problem with the data lake, to me, is it has a lot of distractions, these well-known systems problems that prevent you from doing the work you really want to do. So at the top, we don't have atomicity. Atomicity is this really nice property that when something happens, it either happens completely or not at all. And if something goes wrong in the middle, we can roll back. So it's as though it never happened at all. It makes it much easier to reason about partial failures in a distributed system, and you don't get that when you're just putting things in a file system. Another problem is there's no quality enforcement. This is just a directory. Anybody can dump any data into it, independent of whether or not it matches the schema of that table. And then when you go to read it, it's going to make your program crash. And then finally, there's no consistency or isolation. Anybody who's modifying it sees things as soon as they happen, whether or not it's partially done or not done at all. You can put something there and roll it back, and you won't see it at all. And this means that it's impossible to mix streaming and batch on the same data set. It's impossible to do modifications while you're reading from it. And all of these make it much more complicated to do your job. So let's try it instead with Delta Lake. And the idea of Delta Lake is we're going to take this very complicated architecture and switch it to something like this, where you're thinking mostly about data flow rather than about these systems problems. And why are we able to do this dramatic simplification? Well, the primary trick is this thing called ACID transactions. This is a trick that databases have had for many years. ACID stands for atomic, consistent, isolated, and durable. So we have that nice property of atomicity. When something happens in Delta, it either happens completely or not at all. If something goes wrong, Delta automatically rolls back that transaction as though nothing had happened. Consistent and isolated mean that everybody will see a consistent snapshot of the table, even if other people are modifying it at the same time. You will always see the correct answer, and it will be as though nothing is happening. It'll also be as though people are taking their turn one at a time, even if they're operating concurrently. And then durable means, of course, we're not going to lose data. Now, another kind of key thing here is if I was going to collect petabytes of data that was incredibly valuable to my organization, I would now want to put that in some black box, vendor-specific format, where if I want to read it with other engines, I need to do a very expensive ETL process. I would want to keep it in an open source system with open standards. And so Delta is a full Apache license project. We actually just created a sub-foundation under the Linux Foundation to be a kind of permanent vendor-neutral home for that code base. The data itself is actually stored in Parquet, which is another Apache project, so it can be read by other engines, and there's a growing community around it. So it works today with Spark, but we're also working with Presto and Hive and NiFi and a bunch of other engines for support as well. And of course, today, though, it is powered by Spark, and it deeply integrates with Spark APIs. So whether you're doing streaming or batch, it's very easy to take your existing Spark programs and translate them to Delta, and I'll actually show you in some examples in a couple of slides. But now I want to simplify this picture a little bit and talk about something that I've seen emerge. Once people stop thinking about these systems problems and start thinking about their data quality, they start to develop this new vocabulary. And you come up with these data quality levels. And the important thing here is your data is going to start out as garbage, but what Delta is going to do is it's going to give you the tools to incrementally improve the quality of that data until it's actually ready for consumption. So these are not specific features of Delta. You do not have to have a bronze, silver, gold table or one of them. You can have 10 bronze tables and 1 gold table and skip the silver step. But still, I think this vocabulary is very interesting for communicating to others in your organization the quality of the data that they're working with. So starting at the beginning, we have bronze. So bronze, it's still on fire. It's a dumping ground for raw data. And you might say, wait a second, why am I even storing this raw data? Why don't I just start by ETLing it? Well, there's a kind of interesting reason for this. And that is there are no bugs in a parser that you don't write. If you just keep the raw data, there can be no mistakes in your ETL code. You can always go back to that original record and start from scratch. And Delta supports keeping large amounts of data. So many of our customers actually use it to keep years and years worth of data. We've had people switch from other systems where they were able to store maybe a week or a month, and now they're keeping 3 to 4 years worth of data. And that's actually very powerful, because you can now go back and realize that things you didn't even know were interesting actually are. So after bronze, we get to silver. This is kind of the first step of cleaning. You've maybe parsed out some JSON and made it into top-level columns. You maybe joined with other interesting data sets to augment it. You maybe filtered out bad records or things like that. And again, you might be asking, wait a second, if this isn't my final answer, why is it useful to create these silver tables? And there's actually a couple of interesting reasons for this. One is, first of all, you might not be the only person that could benefit from this partially clean data. A silver table is a very useful forking point for everybody in your organization to get access to this partially clean data and do interesting things with it. But another more subtle one that actually surprised me, but I've seen a lot of people get a lot of value from, is silver tables are great for debugging. When something goes wrong at the end of your pipeline, it's very difficult to figure out where did these bad records come from. But when you have a silver table that is kind of this intermediate result, and you have the full power of SQL to ask questions about it, it makes it much easier to understand where things went wrong. You can ask questions like, and how many rows is this column null? Or how many distinct values are here? And you'll see things that surprise you. And I'll talk in a couple more slides about some really cool things that we have coming for this kind of the data quality concerns. And then finally, we get to gold. These are clean, high-level business aggregates that mean something to somebody important in your business. It's ready for consumption. You can connect it to your favorite tool. So if you have Tableau or Power BI or any of those kinds of things, you can connect it directly into your Delta Lake. You can query it with Spark. You can query it with Presto. We are working on support for Athena, and there's also a pull request for support for Redshift Spectrum as well. So now that we've kind of talked about the different quality levels, I want to talk about how people move data through their Delta Lake, because this process of ETL is something that needs to happen continuously. And something that I've noticed is a lot of people start using streaming here. And I might hear a lot of you thinking, I don't need streaming. That's too complex. I don't have low latency requirements. I don't want to deal with that. And I actually think that's the wrong way to think about streaming. To me, low latency processing is one cool thing that streaming can do. But what streaming is really about is incremental computation. It is this problem of I have a data set that is always changing, and I have some interesting transformations that I want to happen on this data set, and I want that to just happen continuously. And I don't want to worry about a lot of the kind of system control flow details. When you think about ETL, think about the things that you have to do. Part of it is data transformation, but the other part is figuring out what's new and what's old, what's already been processed, and taking that new data and moving it downstream transactionally, guaranteeing exactly one semantics. Don't introduce any duplicates and don't drop any data. Make sure you checkpoint your state so that if things crash, you can pick up from where you left off. And those are all things that structured streaming can do for you automatically. And there is a really nice kind of cost latency trade-off that you can make using structured streaming. So if you do have super low latency requirements and you're willing to pay for it, you can run structured streaming in what's called continuous mode, where we actually grab a core, we are continually pulling from the source, and you can get millisecond latency, which is pretty fast. However, you're going to pay for that, because that core is reserved for that one query. And even if no data is coming in, it's going to be kind of just sitting there, eagerly waiting for new stuff to come in. So what many people choose to do is they run in microbatch mode instead. In microbatch mode, what you do is the stream will actually be processed in tiny little increments, multiplexed across the resources of your cluster. So now you can get seconds to minutes latency, but have many queries sharing the same set of cluster resources, which can dramatically reduce your cost. And then finally, at the far side of the spectrum, there's also this thing called trigger once mode. Trigger once mode is great when you have data that arrives once a day, once a week, once a month. Instead, in trigger once mode, instead of running continuously, what happens is you start up your cluster. This is great because you can take advantage of the elasticity of the cloud. Start up your cluster. It processes everything that is available right then, shuts down, and you stop paying for it. So now you can get these benefits of streaming, where you don't have to worry about the control flow. You can only worry about the data flow, but also take advantage of the cost benefits and elasticity of the cloud. Now, so I've talked a lot about streaming, but of course, Delta is not an only streaming system. Batch jobs do happen. And so Delta has full support for the batch APIs of Spark and also standard SQL DML as well. So you can run update, delete, and even things like change data capture with merge into. This is great when you want to do things like GDPR, or when you have kind of regulatory requirements where you need to have a retention. So you need to say, I can only keep data for 2 years. Delete from where date is greater than 2 years ago. And this is actually very powerful. And all of these operations are completely transactional and can be mixed and matched on the same data sets that you're doing streaming on. One final pattern that I want to talk about is the ability to do recomputation. So the really nice thing about using streaming and keeping all of that data in your bronze table is when something goes wrong, you can actually recompute from scratch. And it's actually very simple. Because when you start a stream from scratch, the way it works is it starts by taking a snapshot of a Delta table. It breaks that snapshot into a bunch of little pieces, processes them incrementally, and when it's done processing that initial snapshot, that backfill, it'll switch to tailing the transaction log and computing the answer incrementally. So what you get is the same answer as though you had run a batch job on the same data set. So this means that when you find a bug in your code, or when there's some new interesting analysis that you want to do for the first time, all you have to do is start a stream with a fresh checkpoint, and it will eventually compute that answer for you, and then continually keep it up to date. This is another place where you can take advantage of the elasticity of the cloud. When you're running that first initial backfill, I'll have customers scale up to 1,000 node machines. They can get it done in a half an hour. And then when they're done with that kind of backfill part, they'll scale it down. And in Databricks, we have auto-scaling. They'll kind of do that work for you automatically. So that's a lot, kind of about what Delta Lake is. I want to talk a little bit about who's using it. And then, as we talked about before, we'll have Kyle come up in a little bit to kind of talk about his use case as well. So while Delta Lake was just open sourced in April, it's a relatively young open source project, it's actually been a product inside of Databricks for the last 2 years. So it's used by, this slide is a little out of date, almost 4,000 organizations worldwide. And we processed over 2 exabytes of data last month alone. And that's just on Databricks. I don't know what's happening in open source. And I want to talk about one particular use case that I thought was really cool. So this is Comcast, and I'm sure you're all familiar with them. But they have data from all of their customers who are sitting, clicking their remote on their couch. And they want to figure out what their content journey is like. So they want to know you're watching the home shopping network, and then you switch to ESPN, and then you go back to the home shopping network. They want to understand what that's like. So they want to do this segmentation job. And they've been using Spark to do it for years. But they have a problem. They have too many customers. And this meant that this job was so big that it would not fit into the Spark scheduler. It would just tip over the scheduler with too many tasks. And so they did what any good engineer would do. You take this job and you hash partition it. You take those user IDs, mod them by 10, and spread it out across 10 different clusters. And so now the job is running. Great? Yeah, so that's good engineering. But there's a couple problems with this. You now have 10 clusters to manage, 10 clusters to pay for, 10 sets of logs to deal with, 10 sets of errors, 10 sets of schedules. It just massively increases the cost and complexity of your system when you have to do this kind of scale out. By switching to Delta and using some of the kind of cool tricks that we have under the covers for scalable metadata management, they were able to reduce this into one Spark job running on one cluster and also cut their cost by 10x as well. And that is a dramatic savings, not only in engineering time, but also in your cloud costs. And so I think this is kind of a pretty good example of what people are able to do once you have transactional, scalable metadata. So if you're interested, you might be asking, how am I going to use this thing? And it turns out it's very simple to get started with Delta. So it's published on Maven. So if you have an existing Spark cluster, using it is as easy as using the -- packages argument. You can see here over in the corner. That will automatically download Delta and install it on your cluster. It'll update on all the things. I would also recommend, I see a lot of pictures being taken. There's a great getting started guide on our website, which I'll show you at the end, that is even better than this. But you can include it in your projects if you're using Maven. And finally, changing your code is trivial. If you're using the data frame reader and writer, all you need to do is change JSON, CSV, ORC, whatever you're using today, to Delta. And you'll automatically get all of the benefits of transactions and not have to change anything else. One thing I want to talk about before I go into the kind of nitty-gritty details of how Delta works under the covers is something that's in progress, just to give you kind of some future looking where the Delta project is headed. So everything I've talked about, transactions and scalable metadata, that's great for making sure that your code runs correctly. But it doesn't help you if there's a bug in your code. And so we have some cool things coming on called declarative pipelines, where the idea is once people start using Delta, they often have one table in one stream, then 10 tables in 10 streams, then 100, then 1,000. And this becomes a nightmare to manage, to deploy, but also to test and reason about the correctness of it. And so the idea here is rather than thinking of all of these tables as independent jobs with independent streams running on independent clusters, what Delta Pipelines does is it gives you this thin DSL on top of Apache Spark. So you're still using the APIs you know and love, data frames in Scala, Java, Python, or even just pure SQL. So you don't even have to do any programming here. You can kind of declaratively specify your entire data flow graph, from those bronze tables to those gold tables and the dependencies in between them. And so as you can see here, I'm kind of defining a data set called warehouse. The actual data set is defined just using data frame code. So just Scala, Java, Python, or even just pure SQL can go there. We can specify details about how I want these tables to be materialized, what bucket they should go in, whether or not I want strict schema checking. So Delta actually has kind of two modes for schema management. We can either do automatic schema management, where as new columns appear, we just automatically add them to the table. This is great if you're ingesting JSON data into a bronze table, and you kind of just want everything to be there. However, if you are kind of at your gold tables and you want a little bit more quality enforcement, you can also do the standard DML thing where you need to call alter table add column if you want to modify the table. And we support both of those. And then finally, you can register Delta tables in the Hive Metastore, so they're discoverable by other people in your organization. And you can give them human-readable descriptions, so people can understand what is this data, who owns it, where did it come from. And so it really helps with data discovery. And then finally, my favorite feature is this really cool thing called expectations. Expectations allow you to take your notion of what quality means and put it into the system. You can take that extra domain knowledge that you have and tell the system about it. These are very similar to invariants in a traditional relational database. So in this example, I'm saying, I expect that this table will always have a valid timestamp. And a valid timestamp doesn't just mean that it's present and it has a year, month, and date. I know that Databricks started in 2012. So if data from 1970, for example, shows up, that's almost certainly a parsing error. Somebody cast a 0 into a date. And so we can actually kind of put those there as these constraints. And you have this tunable severity slider where you can decide what happens when an expectation is violated. In the earlier bronze tables, typically you just want to be alerted. If more than 10% of the data doesn't parse, let me know about it. Or in the gold tables, you might want that you're reporting to some regulatory agency, you might want strict enforcement. Any transaction that adds bad data should be failed, and an alert should be raised. So never let bad data into this table. And then finally, my favorite version of this is this thing called data quarantine. In a data quarantine, what we do is basically when a record that is seen that is unexpected, rather than stop processing, we will let processing continue, and we'll just divert that record into a quarantine table, where you can come and look at it later and figure out how to fix it. So like I said, this is kind of forward-looking. This is something that we're hoping to release in the next 3 to 6 months. So stay tuned to GitHub for more. But now to kind of close out my part of the talk, I want to talk a little bit about the nitty-gritty details of how Delta actually works. Because scalable metadata and full ACID transactions in a distributed system sound a little too good to be true. But it turns out there's actually a couple of simple tricks that we use to get it. So starting off, Delta on disk looks exactly like your data lake today. It's just a directory that contains a bunch of files, with one important difference. We have a transaction log. And inside of the transaction log, there are a bunch of different table versions. So as you can see here, this directory delta log is our transaction log. And each entry is a separate file. So we create version 0 of the table, and then we create version 1 of the table by adding files into this directory. And then alongside of this, we have optional partition directories. I say that they're optional because these are just here for your kind of own debugging. The actual partition information is stored in the transaction log, and that lets us do really cool things. You can even take Delta and modify it to work extra good on S3. So for those of you who don't know, S3 kind of has 2 different tiers. There is this ranged partition metadata tier, and then this hash partition data tier. And a best practice, if you are going to overload S3, is to make sure that the ranges that you're producing are random. So an anti-pattern is actually to every day at 12 a.m., create a new directory for that day and flood it with new files. S3 does not like that. You can overload it. So Delta has this mode where we'll create random partition directories to kind of avoid that anti-pattern. And we actually have overloaded S3, which I think is kind of crazy. And then finally, data files, which are just stored in standard Apache Parquet, can be read by any of those existing tools. So what actually goes into the transaction log? The transaction log is a set of versions, and each version contains a set of changes from the previous version. And by playing the whole transaction log forward, you can come up with the current state of the table, which is the current metadata in the list of files. And so the type of actions that can go into a transaction are you can change the metadata. So you can change the name, add a column, do something like that. You can add a file. And along with that file, you can also add optional statistics like min and max values for each of the different columns. Those min-max values let us do really cool things like data skipping. In one particular use case, we had a customer who was storing trillions of TCP connections into a database every day. And he wanted to be able to very quickly find connections between two computers. So where source IP equals this and destination IP equals this. Using these statistics, we were able to skip 97% of the data in the table, which took a query that would take hours and made it run in seconds, which is super cool when you're doing ad hoc analytics on your data lake. And then finally, remove file, which can take data out of the database. OK, so that's kind of the high-level structure. Now, how do we get those ACID properties? So starting with A, Atomicity, we're going to play this kind of cool trick. So we already talked about how changes are stored in these files. And each of these files is an atomic unit. So each file is a transaction, and files are atomic. But now we have this problem of how do we create files atomically? Well, fortunately, we have this really nice primitive on S3. When you do a put to S3, you start by saying, here's how many bytes to expect. And then if it doesn't get that many bytes, it doesn't accept the write. So that means you kind of get Atomicity automatically out of the box. On other file systems like HDFS, we use transactional rename. We create a temporary file, and we rename it to its final destination. And so now we have this really nice property. Let's say we have a table that has two small Parquet files, and I want to do compaction. I want to collapse those down into one bigger, more efficient Parquet file. Well, it would be a disaster if I removed the files but didn't add the new one, or if I added it but didn't do the remove. But now, because we create this file atomically, we are guaranteed that that compaction will either happen completely or not at all. OK, so now we get into the consistency and isolation. So in order to have consistency, we need to have a serializable schedule. We need to agree on what order changes happened into the table. So just to give you an example, user 1 can create version 0. User 2 can create version 1. But they cannot both create version 2. If they both try to create version 2, one will win. But the other person has to get a file already exist exception. This is something that S3 cannot give you. The S3 documentation pretty clearly says this is not a lock service. We do not make this guarantee. Multiple people can put, and they will both get a success. So we need some other system on the side, Dynamo, MySQL, something to mediate between these. On systems like HDFS, it just works out of the box. Transactional rename can be set to fail if the destination file exists. And then finally, you might be saying, wait a second. If every time something goes wrong, it just fails, then I'm not going to get a lot of work done. It sounds like I have to deal with a bunch of systems problems again. Well, fortunately, we have this really cool trick called optimistic concurrency control. And the idea is this. Let's say, for example, we have two users streaming into the same table. How are they going to mediate with each other? So what's going to happen is we're going to follow the following algorithm. When they both start streaming, they will start by recording the start version. So OK, I'm streaming in, starting at version 0 of the table. They will record what reads and writes they do. So in this case, they read the schema of the table to ensure that the data they're writing matches that schema. And then they speculatively write out Parquet files. So they create a bunch of Parquet files that will be the data of this transaction. They are not part of the table yet, even though they are written out into the directory where the data is stored. And then they go to commit. This is what actually makes them visible to other users of the table, creating that transaction log entry that adds them there. In this case, user 1 won and user 2 lost. But fortunately, what user 2 is going to do is we're just going to check. And we're going to say, OK, wait a second. What happened in version 1? Does it change anything about the state of the world that I care about? And in this case, it doesn't. I only saw the schema of the table. The schema of the table is not changed. I cannot know whether or not I happened before or after transaction number 1. So what the system will do is it'll automatically reorder these things and try again. And so everything will work, and you won't even know this happened. And then one final cool trick is massive metadata. In your data lakes, you often have tens of thousands. I've even seen hundreds of millions of files. And that starts to become a scaling problem in its own. You're starting to have a big data problem even with your metadata. And we have a cool trick here, which is let's just treat metadata like data. We already have a big data system here. So the Delta transaction log is constructed in such a way that you can actually use Spark to process it as well. So we'll take all of these actions from the transaction log, the adds and the removes, and we'll load them into Spark. We'll do a big shuffle to reconcile them. And then we'll write the result out as Parquet in what's called a checkpoint. A checkpoint is the snapshot of a table at a specific version. It's basically shortcuts having to read the entire transaction log up to that point. And the really cool thing is, since it's written in this nice binary encoded efficient format Parquet that Spark can query, you can now do filtering on the metadata very quickly. So in that case before that I was talking about, where we have trillions of TCP connections, and we want to very quickly sort through them, we can actually just scan through the statistics in the checkpoint to decide which files are relevant without ever actually reading the data. And like I said, that can reduce the time to run a query from hours to minutes in some cases. So very quickly, I want to talk just a little bit about the roadmap. Since this is a relatively young open source project, so we just open sourced it in April, but my goal is to have full API parity between everything you can do in Databricks and everything that's available in open source. And so we kind of started with adding support for Amazon S3. We added support for update, delete, and merge. And with Spark 3.0, we're going to be adding full support for create table, alter table, all of that DML. There are also really cool pull requests open to add support for Redshift Spectrum and Athena, so that you can use those tools to read from your Delta Lake as well. So I just want to put this up here. This is the kind of Delta website. I encourage you to check it out. Come join the Slack channel. I have a team of 10 engineers who spend all day sitting in the Slack channel answering questions about Delta. There's also a great getting started guide that shows you how you can start writing Delta programs today. And with that, I'd like to invite Kyle from Cabbage up to talk a little bit about how he's been using Delta in production.
Awesome. Thank you, Michael. While we get Kyle set up, two things I just wanted to share with everybody. You can find out more at the Databricks Booth, which is number 416. If you go over to the expo, you can also sign up for our party tomorrow night. The other thing is that we have 6 hours of free training on Databricks, Delta, Spark, all available on our website. If you go to databricks.com/AWS, on that page you'll find links that'll take you to that, and also other customer sessions and webinars and stuff. I think you're all set there.
All set.
Thanks,
okay.
Kyle.
Great. Can everyone hear me? Yeah, I think you can. I can hear myself. So, all right. So my name is Kyle Burke. I'm the head of data platform at Cabbage. Today I'm just going to talk a little bit about our architecture. We have a data lake. We've been using Delta for I think about a year now. This is the second data lake I've built. The last time we didn't use Delta took about a year and a half. With Delta, I think we started rolling out kind of our top priority things within like 3 months. So it absolutely makes things easier. So we'll dive into that a little bit. And I apologize, my slides aren't available. We'll do the best we can here. So I'm going to talk about our previous platform and our new platform to make a little sense when we start talking about the data lake and why do we build a data lake. Because it wasn't all, usually when you see these presentations, it's all about how everything is great. I'm going to share about all the challenges we had, and why do we build it. So I think it'll help people. I'm curious to see if people are in the same boat. And then I'm going to talk about real quickly about some Delta optimizations that we use that are very helpful, because our goal was not only to make data available, but our users wanted data to be more accessible quicker. So there's this optimize function that's very helpful that we'll talk about a little bit. And lastly, I'm just going to talk a little bit about batch and streaming, because we actually use both. We take a stance as unless we don't want to incur the cost unless there's a real reason, but we do actually have a few reasons. We're up to 5 or 6 streams that are running now, and I'll go over one example that talks about how we made a decision. It actually is valuable to have this data in real time. All right, so first I want to talk about. Oops, I just got ahead of myself here. First is, who is Cabbage? I just want to talk about it because it'll help understand why is our data exploding so much. And basically what Cabbage is we have an automated platform to do small business loans. We will make decisions about whether to extend a loan to somebody within a few seconds. We actually have a spinner on our website, and we spin it for 10 seconds because we want people to think we're taking all this time to make the decision. But we connect to their data sources. We import them. They may be like Wells Fargo, it may be Amazon, it may be PayPal, all different sources. We import them. We run some machine learning models on them to decide their revenue and expenses, and then we'll make a decision and fund them within 10 minutes. So the nice thing about for small businesses, and it's kind of in line with what AWS is saying, is we feel like we do what's right for the business. If you look at the small business market right now, what happens is these smaller businesses, 20 or less, it's incredibly hard for them to get loans. Typically they can't get them, and if they do get them, they want them to take much more money than what they need. What we're trying to do is just give them the amount of money they need and not any more, to get them right at the last minute. We actually have a like a model that we're doing right now that are predicting when people's balances are going to go too low, and then we can fund them money right away, but only the amount they need. So it's very helpful to small businesses. It kind of helps them manage cash flow, and that's one of the number one reasons small businesses go out of business. They don't manage cash flow well. So we look at ourselves as trying to help them out to do this. The problem with taking in all these transactions is it's a ton of data. We have about 200,000 return customers that are happening all the time, and we're getting all their transactions every night. Going back 2 years, we have about 1 million people that have signed up, so we have all their transactions. So we had this kind of explosive growth of data, and we had to figure out how to use it effectively. In essence, we were doing some things Michael was saying. We were cutting it off at a month or cutting it off at 3 months. But in our Delta Lake, our data lake now, we have 2, 3, 4 years from a lot of our clients. Other things about Cabbage, just to let you understand the scale. This year we'll do $3 billion in loans. To date, we've done $8 million. We've been in business since 2011. We're based out of Atlanta. We have offices in San Francisco, New York, and Denver, and Bangalore. Oops. So I'm going to need you to, I'm going to have to keep Thank you. All right, so to compare our old platform, new platform, we were very SQL Server heavy and MapR heavy. We kind of break the world up in our real-time system, meaning like people are on our website, and then our batch system, which people are doing analytics. We were using MapR streams. I got to Cabbage about a year ago, less than a year ago. Their real-time system was trying to implement MapR streams, and their batch system was trying to do all SQL Server. We had other minor stuff, but in essence, we were a hybrid. We had some on-prem and some in the cloud. The new system is all completely in the cloud. One of the biggest problems that we were having is that between MapR and SQL Server, it's very labor intensive. When I talk about like trying to keep all this going, the biggest problem I saw in our environment is that at the time when I started, my team was like 12 people, and they were all data engineers, and they were spending all their time trying to keep servers running, and that was not what the point of their jobs were. The point was to deliver data that was valuable. So we had to come up with something that would allow them to kind of focus on what they were good at. Some of the side benefits, the cost. When I just talk about software and hardware, we were spending about $2 million a year. When we look at a new platform, it's going to be somewhere between $1 million and $1.4 million. So we're going to actually save money and actually deliver more value. So that's the cost is nice, but actually delivering the data that our business needs was the challenge. I can't have the slide up here, but I think it would be helpful. Is we actually had 4 SQL Server environments. We had our runtime system, which was everyone on our website. We were a monolithic company where everything was in this one big database, hundreds of tables, huge environment. We've been switching to more of microservices, which has been going very well. We actually had to take our EDW, put it on another server that was separate, and we got to the point where only our jobs were running. People weren't actually hitting our EDW on that cluster because we were replicating all the data we had a offshore server that everyone from offshore would use, another server, and then we had a US analyst server. So we had these 4 instances running, which sounds great when you first start, but then you have these problems because we were using transaction replication and we're using SSIS to move the state around. And what we end up having a problem is that one server would say one thing and then one server would say another. We'd be constantly getting Slack messages saying, hey, the data in this server doesn't match this server. Oh, let's go check. Oh yeah, oops, we didn't catch that. That data didn't replicate fine. So we were dealing with those sort of issues all the time. And then we got into a situation where we have years of transaction data, 9 years basically of transaction data that we can use. So we started deleting data or splitting tables, which was our latest tack, where we'd have just the last 30 days in one table, and then we have this other server that would have all the historical data. That got real. People didn't like that because it got complicated. We'd start seeing these crazy queries running against our SQL Server that we literally had cases. I was in Bangalore in May, and one guy said to me, he goes, I come in every morning an hour before everyone else. And I'm like, why do you do that? He goes, because if I run this one query, it'll take an hour to run it before everyone gets here. But if I run it when everyone's here, it'll take between 5 and 8 hours. So I was like, wow, that sounds terrible. So we sat down with them. This is true case. We took his queries and loaded onto Databricks. We had a lot of data there. The queries were running in 10 minutes. He was like ecstatic. That was the nice thing, is that we had this kind of group that wanted a new solution. So that's what made it easy to migrate to the data lake. Second piece I'll go through, like our real-time system is really cool. It's all like Akka streaming, writes into Aurora database. One of the neat things we've done is with Databricks, we've actually released our first deep learning model that actually predicts when people's balances go to a certain threshold. But today I'm mostly going to talk about our data lake because I think that's what everyone is kind of here to hear about. So what we're doing now is we're unloading some data from SQL Server. We have a lot of data that just gets written to S3, and as Michael was talking, like our copper tables, any sort of decision we make, any sort of transaction automatically goes to S3. The problem is it's millions and millions of files, and it was almost unusable unless you knew exactly what you were looking for. General person couldn't get to it. So we started taking those directly off S3, concatenating them and combining them and releasing them so that we can basically get rid of this transaction data that's sitting in SQL Server. Other things we were doing is we have a feature store. We call it our metric store because it has metrics and features, data science features. One of the issues data science was having is that when they're training a model, they calculate their features one way, but when they go into production, they may not be calculated the same way because they would kind of throw it over the wall and let the engineers worry about how to calculate this feature. So what we're doing now is we're calculating features in real time, and we just unload our Aurora database onto our data lake. And so the same data that they're training against, they know that those features are going to be calculated the same way as they are in production. So I call it it's like a drift that happens, or now they're not getting at it, where they think it's going to go one way and it's going to happen another way with the models. Other things that we do, let's see, what else am I forgetting about? We have a bunch of first-party and third-party data that's in there. Probably typical all the stuff you guys do. The way we make it available to people is we actually let them use Databricks. And I'd let it open. I said, if Databricks is for you, use Databricks. If you're just going to do SQL queries and you're used to going to SQL Server, we make it available in Athena. Databricks released a feature to basically let your Databricks files be available, like your Delta tables available as manifest files to Athena, so you can easily query Delta files in Athena and Databricks. So Athena is actually a little bit cheaper, so I would love it if they would use it, but we're seeing like a huge spike in our Databricks use just because a lot of our people they want to do Python, they want to do SQL. It's not just let me run this query. It's like I have to string all this stuff together now. So that's why Databricks is taking off for us. We also use Tableau a lot. One of the things that we started doing is we were trying to simplify our stack. So almost all of our Tableau reports directly go off of Databricks. And there are certain cases where it's not fast enough because we're not using the most recent version. But most cases it's fine, but the way that gets through it is that Tableau allows you to do extracts. So we basically, if it's a really high throughput case, we just do extracts, and we've been really successful with it. Other cool things we do model monitoring, things like that. When we unload, when we're actually doing our feature store, we actually write metrics about the model to the metric store. We unload them, and then Tableau can read those, and we've got a bunch of cool graphs about how our models are performing. And lastly, we kind of, to tie it all together, one thing that we we use Airflow. We like Airflow a lot because our current SQL Server has about 300 jobs that's running. And that's it. As soon as you get to the point where you have a lot of dependencies, it's really hard to kind of manage it in Databricks. But with Airflow, you basically get this DAG that shows you everything, all the dependencies. So if you're changing something upstream, all the potential downstreams, we know it gives us a way to test when we make changes. So it helps us out a little bit. All right, so I'll wrap up real quickly. Some of the Delta table optimizations, it's really, the one thing that I'll say is before Delta, we basically used partitions. Partitions was our way to kind of make things fast. So I had a case where we were doing, we had a very large data set with day, hour, and geography because we had a lot of time-based geography type of queries going on. Thought that'd be great, thought it'd be fast. The problem what we ended up running into is that ended up with too many files, too many partitions, and Spark spent all its time looking for files. So now we had very simple with our partitions. Almost everything is by day, and then we use the indexes. There's a function, optimize. There's a couple different ways you can use it. You can say optimize table, and what that'll do is it'll basically take all the small files and turn them into big files. We have an example that one of my engineers just sent to me. Had some old code. We hadn't really looked at it in a long time, and people are telling us it's running much slower. So he went in, he just ran optimize table on it, and he sent me the results. And basically, before the optimized table, the Spark said that it was reading 150,000 files to actually return the query. After he ran optimized table on it, it ran 500 files. So it was like a 40-50% improvement in speed just by doing that one command. So what we've been doing is, one of the nice features is, because we're loading things generally by day, there's like, you can put a where clause on it, and basically it's where by partition column. So every time we load it, then we just run optimize by partition, and it keeps up to date. And that's something we just started using. It's super easy. We also had an interesting use case. I wasn't expecting this, but when we're trying to move everyone from SQL Server off into the data lake, I sort of think of data lakes as, hey, we want to aggregate some data, we want to run some queries and things like that. I don't really want to do these single user lookup things. But in actuality, we had that case. We had customer support that actually needed to actually look at a particular business and see all their transactions or see whatever. So our transaction data are our biggest ones. So to move our customer support off of SQL Server onto our data lake, we had to optimize to let them quickly look up transactions. So we did a test. We had a table with 750 million records in it, and we wanted to be able to very quickly look up all the users' transactions. So before we put optimize on it, we were doing some tests, and it generally was between 1 minute and minute 30 seconds. So we just felt like people would get, generally what people said is, if this thing takes more than 10 seconds, I'm bored and I move on. So we ran optimize on it, and the same query that was taking that long only took 3 seconds. So it gave us the confidence that, like, hey, we actually have the ability for all these things that we don't anticipate. We have these kind of very simple tools that we can kind of use to basically meet the user's demand. All right, so the last thing I'll talk about real quickly is batch and streaming. As I said, most of our stuff is batch. We're getting into hourly. Like, hourly is kind of the most I generally like to do until we can get more of our data out of SQL Server, because a lot of our data is coming from SQL Server, and if we're going every hour hitting it, we're actually putting a tax on it. But there are cases where the data is not coming from SQL Server, and at that point, it doesn't bother me that much. And one example is we have a streaming application that basically, every time somebody's on our site and they may like add a new bank or they can do anything, we have this event stream that comes in that we write to a Delta table. And our application developers write to about 10 different topics. It could be a channel ad, it could be wizard completed. Like, all the events say, website _ event _ and then it gives a different name. We take all those events, like 10 or 15 different topics, we stream them all into one table, into one Delta table. And then what we do is, what's nice is that if somebody is going through our wizard and they fall out, we actually can follow up with them. And the way we do that is basically we read this event table, and then we stream these events. We enrich it with things like what is their revenue, what is their expenses. And what that helps us do is it does a couple things for us. One is we have 3 different sales teams. We can stream the event to the right sales team, Salesforce. Second thing we do is, at any time, there's thousands of people that we could call back at any one point. But we want to call back the people we think that are most likely to qualify. So now with this additional metrics that we're putting on this event stream and Salesforce, now we can order them based on some of the things like maybe revenue, or we have some data science scores that we call, and we score them, and then that goes into Salesforce. And now our sales team is actually focused on calling the people most likely to qualify. And it's helped with driving. That's why we were growing by like 40%, is because we're very focused on calling the right people. So yes, it is a little more expensive to do real time, but it's absolutely worth it in that case. So we have like 4 or 5 of those use cases that are helpful. And that is it.
So Kyle, obviously you guys are doing some really cool stuff. First off, how can people get in touch with you if they want to find out more or get engaged with you in terms of learning more about what your team's building?
Sure. I'm on LinkedIn. My LinkedIn is, just look up Kyle Burke at Cabbage. I should come up. Go to cabbage.com. The one thing is I do these talks, and my company tells me to go do these talks. It's basically we're hiring. So we're trying to hire like 50 people next year, which sounds like our HR people are going out of their minds thinking how they're going to hire 50 people next year. So go to the Cabbage website. There's all different areas of IT that we're looking for. So
yeah, and we'll definitely put a link to you in the blog post. As I mentioned, we're going to do a blog post here at the end of the week, recapping everything. One of the things you mentioned was the Tableau connector. And so in 2019.3, the latest version of Tableau that released, there is a new optimized connector. It's 30% faster, and it now connects to specifically to Delta Lake. So that's just one thing if you're using Tableau. What's kind of your timeline for upgrade? When are you guys thinking you're going to move to 2019.3?
So the issue that we have is Tableau Online doesn't
right.
support that yet.
Okay,
so we're
so
waiting
that's
for
coming.
that. That's
Right.
coming very soon.
Okay.
We looked at, the reason we do Databricks and Tableau and things like that is we're trying to get out of like everything roll our own. And so as much as we want that new Tableau thing, is we don't want to bring that in-house and have to manage it. Like we had too much issues trying to keep servers running that I'm very much like, hey, if they give me an online version, I'm going to use that because it helps us focus.
Makes sense. Have you used the time travel feature at all? Is that something that's come up for any of your work?
Yeah.
Maybe you can kind of explain what that is and then talk about how you've used it if that's...
Yeah, that's time travel is basically you can look in like a timestamp on any of the files and say, what did this data look like at this timestamp? And that's basically for data science. We have a lot of cases where as soon as the models aren't performing the way that they think they're performing, they want to go back and look at the data as it was when they actually trained the model to see if something else is going on. So that is generally when it gets used is cases like that.
Yeah, awesome. I mean, and we've had a couple of customers who've had data, sets that have been deleted by mistake and stuff, and they've been able to bring that back. Obviously, if you're looking at auditing, there's another ability of Delta is that ability to time travel and look at data sets that were used in any of your algorithms or any work that you did. So, so that's another great piece. Michael, did you have anything that you wanted to kind of kick in and ask Kyle as well?
No.
No?
But,
Okay.
yeah, sorry.
Okay, we've got about 8 minutes left, so
talked
what
a
I'll
bunch
do is
before.
I'll walk around real quick with the microphone if anybody wants to ask Kyle some questions. Anybody want to raise their hand?
Or Michael.
Yep.
More for Michael. Do you know if there's any plan to support the Impala support the Delta Lake?
Yeah, that's a great question. So the transaction protocol is open source. I published it a couple months ago. Pretty easy to implement. I have not heard any interest from the Impala community, but if anybody wants to, send them to me. I'm on Delta Slack. I've been helping the Starburst people on Presto quite a bit, so I'm happy to answer questions if anybody wants to build that.
Hi. So we have a data lake, and what we're doing is we are using we're using data migration service to get the data into S3, which gets it into CSV format, and then we use EMR Spark to generate the Parquet files. Is that something that I can use Delta Lake for?
Yeah, that's a great question. So you can use structured streaming to read from your CSV files and put it into Delta Lake. That all works with just Apache Spark and open source Delta Lake. The other thing that we have in Databricks is we have a system called auto ingest that's significantly more efficient because what it does is it actually subscribes to notifications for that bucket. So that rather than listing the entire bucket to describe what is new, as we all know, S3 metadata operations are quite slow. You can get maybe 1,000 files a second out of it. It's significantly faster to do this with notifications as well. So either of those work, but it'll be much cheaper to do it. Yeah, so definitely. So the question was, do you support change data capture, including deletes? And the answer is yes. We support merge into, which kind of lets you take any stream of data from anywhere and say what to do when certain conditions are met. So you basically give it a key. So you say merge on this equals this. When it's already there, update it. When it's not there, insert it. When this flag is set to true, delete it. And Delta takes care of all of that for you. And that's available in both the open source and the Databricks version of Delta Lake.
Is the Databricks Tableau connector able to work with the open source version, or it's something that we need Databricks?
Yeah, so the Databricks Tableau connector, which is now supporting Delta, is supporting Delta on the Databricks implementation. So that's really what you're looking at with that 2019.3 release. To be able to hook Tableau to open source Delta Lake, that's something we'd have to look into. Actually, if you come by the booth, we could talk a little bit further about that.
Yeah. You can connect it. We're using the Spark JDBC server,
Right.
but we made a lot of modifications to the JDBC server to make it better. Yeah.
Hello. How do I actually run queries on a the Delta table? I mean, how do I get all these different versions of the table and all the metadata?
Yeah, so I mean, it's just normal Spark. So you can use Spark SQL and write SQL queries against it. You can use the Spark data frame APIs to read from it. And by default, what you get is you always get the current version of the table. But in the data frame reader API, you can also specify which version you want to read when you load the table. So you say like load this table version as of, and you can either give a timestamp or this like version number. In Databricks, we also have a feature in SQL where you can use that syntax in as of, and we are working with the Spark community to push those changes into the Spark SQL parser, so you can do them there too. Yeah, so the stuff that we have out today for Presto and Athena, the way it works, so we only support, so basically for those two, what we do is we create manifest files. And I do not think that it lets you specify which version to create the manifest files, but I could be wrong. But one of the reasons that Starburst is trying to build their own native connector is so they can unlock all these features. Pressure them. Go talk to them and tell them to hurry it up. Tell them you want it. I am here to answer any questions about the transaction protocol to help them build that.
Definitely, if you come by the booth, you can see a bunch of the notebooks that we have that demonstrate a lot of these capabilities. So it's a great way to get a good look at that. It's booth number 416. Okay.
So I have a couple of questions. One is on Power BI. Is there a connector for Delta Lake?
Yes.
Okay.
Yeah, Databricks supports that.
Okay. And then the second question is more about, I would say, enterprise question, that if I have a big enterprise platform with 10,000 jobs running a day, can Delta Lake replace all of that tomorrow?
Yeah, I mean, so now you're venturing into Databricks territory. Like Delta is a transactional storage format for a table. It gives you all of these school properties. It is not a workflow orchestrator. That said, tens of thousands of jobs running on lots of Spark clusters is what Databricks does.
So just to reiterate for anyone who doesn't know, the expo area over at the Sands Expo, which is where the Venetian Palazzo and all those buildings, that's where the main expo is. So if anybody's looking for us there.
Hi, thanks. The updates, deletes, it kind of implied that's on the Scala API only. Is there, or is it on Python too?
No, we have Scala and Python. And in Spark 3.0, we will support SQL as well, hopefully.
Okay, but it is on Python?
It's in Python already.
Perfect,
Yep.
thanks.
Yeah, their slides are out of date. One more in the back.
Hi. How does the compaction work? Is there a process that you guys support within Delta? Because you have all those versions and you probably have a lot of files because you're only appending.
Yeah, okay, so there's a bunch of different questions here. So the transaction log automatically takes checkpoints every 10 commits. That just happens automatically. We automatically clean up the transaction log after 30 days, but that's tunable. In terms of cleaning up old versions that no longer exist, there's a command called vacuum. And so when you vacuum the table, you give it a retention period. By default, it's 7 days. And we will delete any version of the table that is more than 7 days old. Now that prevents you from time traveling or streaming from 7 days before. So your streams need to be up to date within the window that you do it from.
Okay, at this point, we'll go ahead and close out. Big hand for Kyle and Michael. Thank you so much. Great presentation.
Yeah.